Buenos días con todos. Voy a aprovechar este espacio de 2 minutos para hacer mi propaganda. Veo acá muchos alumnos. ¿Han escuchado de la beca ILAB? Algunos de ustedes, ¿no? ¿En qué ciclo están? ¿Segundo, tercero, primero, octavo? ¿Por acá? ¿Quinto? ¿Primero? Ya. Bueno, mientras esperamos 2 minutos, me presento. Yo soy Carlos Montes, trabajo en la Facultad de Ingeniería de la Universidad de Alberta. Y UTEC es nuestro partner estratégico en Perú y hay un programa de becas del gobierno de Canadá que para los que comienzan la universidad de repente más adelante les podría interesar, que son pasantías de investigación en la Universidad de Alberta con profesores durante 4 meses. Son becas que les financia el gobierno de Canadá, así que uno de los requisitos principales es justamente conocer los profesores y qué es lo que hacen. Bueno, acá vamos a conocer un poco más el trabajo que hace Peter en ingeniería eléctrica. Pero bueno, más adelante ya los invito a revisar la página web de la universidad, preguntar en la oficina internacional cualquier duda que tengan con Valeria, Silvana, Gaby, Patti. Y bueno, yo voy a estar acá por 3 años, así que me pueden molestar también, porque tenemos otros proyectos. La beca se llama ELAP, E-L-A-P. Es para pasantías de investigación. Sí. Y para aquellos que ya están terminando la universidad o que van a terminar pronto, hay maestrías de investigación en Canadá también. En caso te guste mucho la investigación y quieras continuar programas de maestría en Canadá, tenemos maestrías en investigación que tienen un componente alto en investigación y maestrías profesionales también, que bueno, son cursos a nivel alto, ¿no? Pero lo principal para cualquiera de los casos es averiguar, investigar a los profesores, porque tenemos profesores que trabajan con tecnologías aplicadas a diferentes industrias, ¿no? Y es mucha información. Bueno, comenzamos, so we'll start. ¿Cómo va el inglés? All good? English? Spoken? French? German? German someone? Deutsch? 9? Francais? It's okay, it's English actually. So thank you very much for being here. I'm going to introduce myself again. I'm Carlos Montes. I work at the Faculty of Engineering at the University of Alberta. Today, I have here our Associate Dean, Professor Peter Musilek. Besides being our Associate Dean, he's a professor in the Electrical and Computer Engineering Department at the University of Alberta. And today he's going to brief us a little bit about what part of his research about intelligent energy systems, mainly about artificial intelligence for the transition and sustainability. So if you have any questions, it could be at the end. But if you don't want it to be at the end, just raise your hand. The same for people who are joining us via Zoom. So without further ado, please.
Thank you very much for the introduction, Carlos, and welcome everybody. I'm excited to share with you some of the work which we are doing at the University of Alberta in my research group. As Carlos mentioned, I am really interested in applications of artificial intelligence in electrical power systems. I'm not power engineer by trade and by training, but I have electrical engineering degree, and I am really trying to connect on the high level. You will see that the applications I'm going to talk about are on the system level, the high performance computing, machine learning, and different types of AI approaches to support the operation and make it more effective for the electrical power systems. Okay. How do I turn it on? It is on, but I'm sure if the battery will last, but we'll try. No. Maybe it's not charged.
It is charged. So I'm just...
Okay. So that's it. Can we try? Sorry about the glitch. It's okay. So you can just control it. I'll let you know. Thank you. So I'll start with a very brief note on why we are interested in this field, right? We have power systems, they work well, but of course, it's all related to what we are observing in the environment, what's happening with the climate. And that's one of the motivators to speed up the energy transition to support it, so we can make the energy systems and power systems in particular more efficient. So we minimize the contribution they have towards the climate change. And I'll describe a number of applications, most of them from our group, but I wanted to make it more holistic to cover different aspects. So some of those will be also by other researchers of data analytics and different types of AI approaches for power generation, power transmission, and power distribution or energy management. I mentioned that the motivation behind this is, of course, the global warming, right? That's something which has been happening for a quite long period of time. We are aware of it. What's interesting that in recent years, the observations and the predictions are becoming even more difficult to see. We can see those two curves. We can see the acceleration. The slope of the curve is getting steeper. And therefore, it's even more important than ever to really make sure that we are not adding more pollution, not adding more greenhouse gases, and not increasing the impact of greenhouse gases on the climate. The implications for energy transition, and we will have a diagram later on which will explain this in more details and with some examples. But in power sector specifically, this transformation will mean several things. One will be decentralization. That's something which we are seeing already today. We see PV panels being installed on houses in residential areas, and we see some larger scale photovoltaic farms and wind farms. But this will become more prevalent, and it won't be just a single smaller house installed PV panels, but really large production plants providing electricity on the grid. This is very different from what we are familiar with, what is the typical model for generation and consumption when there is a large, huge power plant providing energy, which is then being transmitted over long distances and then used in the load centers. The other aspect, the other aspect is increased variability because the energy is weather dependent. We cannot really command sun and wind what to do at any given time, and therefore we have to deal with this. We have to accommodate, accept this variability, and come up with some methods how we can deal with that. This will lead to having really power systems which are different in nature. They are much more complex. They are much more dynamics in how they behave. And therefore, we need to come up with some ways how to coordinate, how to accommodate, integrate this energy on the grid, and how to use it in different sectors, for example, including the transportation sector, industry, and building sectors, such as smart buildings. So this is the diagram I mentioned before. On the left-hand side, we have today's most typical configuration of a power system, when we will have individual power plants, producing large amounts of energy of different nature, and then transmission system, which will provide the interconnection and supply the energy to different end users, whether it's industry, whether it's individual houses in neighborhoods, etc. What's changing and how we envision this system to look in 2050, in next 25, 30 years, there will be a bunch of changes, and we can see them highlighted here using those question marks, for example, and also using some symbols plus. So the question marks mean that we don't really know what's going to happen with the traditional power plants. It depends on many things. There are still unknowns. For example, we can accommodate more renewable energy if we have very significant increases in capabilities of energy storage systems, because today we have storage, but it's not so easy to store energy for longer periods of time. So there is a big progress in that. Maybe many of those plants will not be needed anymore, and we will be okay accommodating more, let's say, photovoltaic energy, because we can store it and then use it, the stored energy, overnight. We can see that there are some pluses as well, as I mentioned. So one is we will have much more renewables in terms of their contribution towards the operation or power generation on the grid. We will have more electric vehicles, and they actually pose very significant problem, a challenge for the power systems. If you look at a typical charger for electric vehicle, they would be, especially for fast charger, equivalent to an entire house. So if you have a house and you in the future would have 2 vehicles, it's like tripling the number of houses, right? And the current system is not really ready for that. How we can deal with that, how we can accommodate those vehicles, etc. There will be other components such as batteries, and we can even consider, of course, something which is very interesting and booming today, such as hydrogen for production and for storage and transportation of energy, which will become part of the system as well. So let's start by looking at some examples from the area of power generation. The first example is actually adopted. This is describing the situation project which they run in Texas in the United States. And they were looking at how efficient is production of energy in those conventional power plants, right? We cannot get rid of them overnight. It will not be economical. It would be disaster economically. And we wouldn't be able to produce alternative energy right now. So they need to continue operating. So the issue is how we can make them to work more efficiently. So there are minimal losses in the conversion of energy, etc. I'm not going to go through details, but this is the overall diagram describing how energy is produced. And there is an important parameter called heat rate, which is a measure of the thermal efficiency of the plant. It depends on a number of factors, some internal, some external. And if we know the heat rate, we can try to set it up on a sweet spot, on some optimal value, which will then make the operation of the plant overall more efficient. So what they decided to do was to look at the historical data, to take a lot of measurements, how the plant operates, what are the operating set points, what are the external conditions, let's say what's the temperature, what's the humidity in the environment, and put all this information together and use some machine learning approaches, specifically neural networks, to process this information and to learn, in a sense, how to control the plant more efficiently. So they took all this information, did a lot of preprocessing for the training, and then in the end, they would be able to deploy this, to use those machine learning-based models to control the set points, to predict the outcomes, and update the recommendations for the operators. So this, in effect, would be able to increase the efficiency of operation of conventional power plants. Yeah, sorry. Yep. No, this would be really just the generation. So it's the power plant itself. So it can operate at the optimum efficiency. You know that if you are running a car, right, it also depends, you have different efficiency depending on your RPMs, etc. So this is very similar. So this neural network will learn how to set the parameters of the power plant, the turbines and the heat, depending on what's the weather outside, for example, right? But it's not, in this case, related to the transmission yet. Thank you. The next issue is, as I mentioned, is related to renewables, and we can expect big growth. If you look at the situation in Canada, there is, of course, a lot of traditional generation, depending on which part of Canada you look at. It will range from nuclear to hydropower plants, gas-powered power plants, and there are some large-scale renewable projects already in place as well. For example, in the province of Alberta, where I come from, most power plants, traditional, were coal-operated. Almost all are now converted to operation based on gas, so gas turbines. But we have a number of large power plants which are powered by wind and photovoltaics as well. In fact, in Alberta, we have the largest power plants for wind. This is related to the geography. We have Rocky Mountains, and there is a very strong region with a huge wind power, so we can take advantage of that. And there is a lot of power plants, wind farms cropping out there. Similarly, for the area of photovoltaic generation, we also are building some very new power plants, which will be largest in the country. I think, yeah, good. I'm going to describe one case, which is similar. It was not really application directly in the large-scale power systems for power generation, but it was how we can think about generating power and rationing power for remote monitoring sites. Right? So it's on a smaller scale, but it's a very good example to explain the principle. And this was specifically based on a project which we are working with colleagues who are monitoring conditions, weather conditions, let's say melting of icebergs and ice fields in Arctic areas of Canada. And of course, those areas are very remote, are very difficult and expensive to be reached. And therefore, if they want to operate the monitoring stations, they have to come up with some way how to power them for as long as possible. They don't want to go every 2 weeks and change the battery, so to say. So we designed a system which, in addition to having the battery, which is the most conventional power supply for this type of applications, because there is no outlets to plug in your converter. We would add a solar panel, but the most important part is in the power routing area. So we have to come up with some way how to decide when to use the energy coming from the solar panels, when to use the energy from battery, with the goal of lasting the station as a whole for as long as possible. So we designed a fuzzy power manager. So that would be, you can see the control surface here, which would take into account a number of things. The important concept here is the concept of duty cycle, which you will most likely be, and some of you familiar with anyway. If I look at the monitoring stations, the specific way how we can implement duty cycles is to change how often I measure something. So there can be some ideal desired frequency. Let's say I want to take a measurement every 5 minutes or 10 minutes. But if you think about it, it's probably better to take a measurement every hour than to take measurements every 10 minutes and then run out of power and not being able to monitor for months and weeks. So this is the duty cycle which will be controlling, and the variables which will be coming into the equation, which I can measure or predict, are the state of charge. So this is something which I can measure. I can see what is the percentage of energy I still have stored in the battery. You know, it can be 80%, 50, 20%. And I can look at predicted energy availability. So how much energy I expect to receive from the environment. And this is something which again can be predicted by some forecasting system, or it can just be estimated based on the climatology. I can look on a typical year, what I can expect in the month of January, how many hours of sunshine in Lima, for example, right? Or how many hours, so it will be worse in northern Canada, believe me, in winter. So those are the parameters which will be entering the power manager. And those are the results of the simulation. So on the left-hand side, we have the conventional approach. And in the first graph, and you can see it's the same on the left and right, is the availability of the energy from the sun. So it's the incoming current from the photovoltaic panels. The second one shows me the state of charge of the battery. And we can see some significant levels here. We can see that at the top, which is around maybe 85%. And at the bottom, there is a limit around 20% or 25%. Each battery should be used sensibly, otherwise I'll deplete it and I can damage the battery. So it shouldn't go all the way to 0 or should be charged all the way to 100%. So this is reflected in those limits. And if you look at this left-hand side, which is the conventional approach, as I mentioned, meaning that I'm doing measurements as often as I wish, that's my goal. I want to measure every 10 minutes. And we can see that at certain time of the year, it will be in the fall in Canada, the state of charge start to decrease. And at certain point, it will hit the lower limit when I won't have energy available to power the system. And we can see that the duty cycle, which is then depicted at the bottom, goes all the way from 100% to 0. So it means that at all those times which are indicated here by those blue lines, I'm not taking any measurements. You know, it doesn't have the details, but it can be hours, it can be days, it can be perhaps several weeks. On the right-hand side, we have the situation when we would use the system which I described on the previous slide. So based on the actual measurement knowledge, the state of charge, and the outlook, the forecast of how much energy I can expect. I can start earlier. That's the power of forecasting and predictive control. I can start early to decrease the duty cycle, but you can see it doesn't go all the way to 0. So let's say instead of every 10 minutes, I'll be taking measurements every 12 or 15 minutes. I'll decrease the frequency of measurements, but I'll still be able to take some within a given period of time. And what happens here is that if you look at this curve, again, it's decreasing, but thanks to our ability to predict what's going to happen, how long I need to ration the energy for how long, I was able to last through the winter, right? So here we would hit 20%, but this is something when I can already expect that the sun will start coming out and I'll be able to power my monitoring system using directly solar panel and start recharging the batteries, as we can see from this increasing trend. So this is something which is an application on a simple system for remote monitoring, but the same principles would apply to larger systems, let's say remote villages which don't have connection to the transmission grid. They would typically today use diesel generation, right? Sometimes it's being replaced by photovoltaic panels, but again, diesel is expensive and it's polluting, but it's more predictable. I can truck in the diesel and I can run it whenever I want. I cannot rely 100% on the sun, but if I use methods like this, I can extend the life. And in many situations, I can rely on the photovoltaic energy solely. Another example of using forecasting is looking at different types of weather-dependent energy. In this case, we are going to look at an example when we used, again, AI-based image processing, in this case, techniques to predict so-called wind ramps. Wind ramps are, again, very significant, very important to know about in power systems. Those are big changes in power generation. You know that it sometimes happens, it's quiet, no wind, and then picks up. And there is a huge amount of power generated by the wind farm, which has to be somewhat accommodated on the power system. This is not easy because the power system really depends. The balance has to be maintained, that you cannot really put the energy there, pile it up, and then use it. So from the perspective of stability and ability to be able to operate the system, it's good to know. So here is an example. You can see one of the curves which goes all the way up here, which shows the huge increase in the average power generation, let's say from this level, and then it goes all the way up here. And we would like to be able to predict those power ramps. So we can do something, right? Whether it's, let's say, decreasing the generation from traditional power plants, which may be connected to the same system, for the up ramps, or turning them back on, switching back on the traditional power systems when I can expect that my ramp will go down, that the wind power generation will be significantly lower. I mentioned image processing, but what kind of image this is? This is actually a pressure map. So we can use weather forecasting models to describe the state of the atmosphere in much detail, and I'll talk a little bit more about it later on. But in this case, we can just extract the values of pressure. And then we can use some image processing techniques to identify some significant changes, and they will help me, in this case, to determine what is the position of a weather front, which will be moving through the countryside. And when I have a location of a wind farm, let's say indicated by this symbol 1 here, and I look how it moves through the time, I can predict when this will actually happen. And we did this. We used real data from the wind farms, and we used numerical weather prediction to generate the values of pressure in this case. And we were able to, with high success, to identify those wind farms beforehand. Again, if you know it beforehand, it's much easier, much cheaper, and much more efficient to integrate that energy on the grid, because I can take preventative actions. I can plan on how I'm going to use other resources on the grid. The second area is power transmission, and I'll show you a few examples. Most of them are again done within my group. When you see case, that's a case which really comes from my lab. And on this illustration on the first slide, you can see something which is not very common in Peru. It's actually not so common in Canada either, especially in Alberta. But there are parts of Canada which suffer from ice storms. So there is a lot of snow which is coming in very wet form, and it then accumulates on the power lines. And because of the weight of the accumulated ice, they can actually be damaged and they can cause widespread outages, which are very difficult and costly to repair. There are ways, again, how this can be mitigated or prevented. You can, for sure, establish, let's say, need for more diesel, so the diesel generators can be powered up and they can support critical infrastructure, hospitals, for example, in the area. But there are even other ways. For example, the lines can be disconnected for a short period of time, and they can be powered in a way that will heat up, and it will help to remove that ice. But again, those are things which are not easy to plan and execute. And if we have the knowledge beforehand, if we can predict when this is going to happen, it's very useful. Just for the general illustration, this is not really commonplace, right? This happens on a significant level once every, let's say, 10 years, right? But it can be very significant. You might have heard or not, I'm not sure, but that there was a relatively significant storm actually about a few months ago. But about 20 years ago, there was a storm which affected Quebec, province of Quebec, and some parts of state of New York, which was very significant. And it even caused some death because people were not able to get electricity for days and weeks because of the widespread damage. It wasn't just like on this figure, you can see distribution system which would be affected, right? It was a good illustration. But there could be the large metal, steel towers which would be toppled down, and it takes really literally weeks to restore the power. So let's have a look how this can be done. I mentioned the numerical weather prediction. This is a user manual for ARV weather forecasting system, which is publicly available. So we actually were able to download it, install it, and use a powerful computer to run our own weather forecast. So this is something which the weatherman on the news would use as well, the outputs of similar systems, but you can run it in-house without any problems. And what we would like to be able to do is to produce maps like this. So again, looking through the geography in the space, what would be the expected amount of ice which would accumulate through this process of ice accretion? So again, wet snow or freezing rain, more likely freezing rain falling down, accumulating, in this case, on the wires of the power transmission lines. There is a number of models, and we selected one ice accretion model, but the problem is how to decide when to run the model, right? As you will see on one of the following slides, this model basically takes the amount of rain which we are receiving, which can be modeled by the system. It contains temperature, etc., but doesn't have any upper and lower limit in terms of when it should be applied. So what we did, we took some data which was available and combined it with the numerical weather forecasting outputs and designed a system which will help us to engage this accretion model appropriately. So only during the condition when it makes sense, when it's likely that this effect of ice accretion will occur. So this is just a general illustration of how the numerical weather prediction works, not really looking inside, but it's basically a set of complex equations and initial conditions which describe the physical dynamics of the atmosphere. And it has many elements. What we typically see, is the temperature and wind on the forecast, but there is hundreds, literally hundreds of variables, not just in the space, but at different levels of the atmosphere going from the ground up. And we can use them, combine them in a way we need to get some information from this very useful data. In addition to this data, we also got our hands on a published study, which actually was taking place or describing an event which took place in Southeast United States. And this study actually contained detailed description of observations of the amount of ice which accumulated at different locations within this area. You can see that most areas are white, but some are a little darker. And this was actually, again, quite significant amount of accretion which occurred, and it caused some damage. It wasn't so widespread, but it was still very significant. So we can here see the numerical weather prediction model, which will give us all the values we may need, the ice accretion model. And what we did to develop this engagement function, we used the data from this study. So this would include location and the record, which was produced by a human observer, a meteorologist, or somebody, a technician who would go and measure the amount of ice which accumulated and when. Right? So it's really very useful data. And when we combined the two, we came up with the following diagram. So this diagram actually shows what types of precipitation was falling, going from freezing rain, which is of our interest, those circles, through rain, which is just liquid. It's not going to accrete, it's just going to run off. Snow, which can be significant, but it doesn't really stick so much as a freezing rain, so it's not so dangerous. And some unidentified types. So this is something which we have to eventually discard. And you can see that this graph has actually two axes. One is temperature, which is something which we are all familiar with, and we would expect that the temperature has to be below zero for freezing rain to start sticking to the surface. But we can see that it's not necessarily only there. There would be cases, let's say, there are some circles here, some circles here, and circles going all the way down to certain value. We can see that there is nothing, let's say, below -4, right? Which is, again, quite important observation. So when it's too cold, we don't have to worry so much. It's really when it's around zero, when this can become dangerous. On the other axis, we have something which is not so common and you may not be familiar with. This is something called fraction of frozen precipitation. It's a one value which I can get from that meteorological model, from my numerical weather prediction model, and which describes what proportion of the falling precipitation is frozen. Normal rain would be 0. There is nothing frozen in it. Snow will be 1. And anything in between will have different capacity to actually start accreting, accumulating ice, and eventually cause damage. So this graph is really looking at what is the distribution, both from the perspective of the combination of temperature and the frozen fraction for each of the observation stations, but also the magnitude, how significant it was, which is signified by the size. So you can see that there are some smaller circles like here, and some larger circles, such as generally along this axis. So we can go to the next slide and see what we came up with, right? So this forecasting model is based on the ice accretion equation, the model which we adopted. It's a physical model really describing, I have rain coming in, this is the temperature, this is the wind, which is also an important variable in that. What's going to happen, right? But in order to be able to engage it, we had to come up with some limits. And we used genetic algorithm in this case, an optimization approach, to come up with limits for a linearly increasing function between 0 and 1 to multiply the output of that ice accretion model itself. And we can see that there are two pairs of values. So one is for I, which is the frozen fraction. And we can see that it goes all the way from 0 to about 0. I would say 90, 95, 96 here. So that would be the winning configuration. So between 0 and 0.96, in terms of the frozen fraction, there'll be 0 to 100% engagement of that model, meaning below that, nothing is going to happen. Above that, it's full. The other one is for temperature. And again, we have some values here. We can see that on this side, it's around minus 8, minus 8.5 for the lower limit, and about plus 4 for the upper limit. So again, the range is broader than what we may expect based on the data which was collected. So this is how we developed the function and how we verify that on the original data. In 2010, we were lucky, and some people were unlucky, because in Eastern Canada, there was an ongoing icing event, and we read about it in the news or saw the news on the screen when it actually started to happen. So they didn't predict it, they didn't announce it's coming, but of course, when it started to happen, it was a big deal because it caused widespread damage. This is the eastern part of Canada. It's Newfoundland and Labrador. It's an island of the East Coast. And we can see a map here, which actually is expressing how likely it is that ice will accrete on power lines. And there is also a piece from the news which said that they had 250 lines and transmission structures damaged. So it's a very significant number. It takes a long time to fix. They also reported that in some cases, ice as thick as 12 centimeters. So this much ice, right? So it's a lot of weight, which is then waiting on those wires and can damage either the wires or the towers. And what we did, we took our model, which was actually trained on a different region. It was a similar event, but in different region. And we applied it, and we found that it was very successful in predicting the outcome, not only in terms of the match. It's not very well visible, but this is 0.2, so this is the 12 centimeter level. The other part, I apologize for not very readable picture, but you can see some S-shaped curves. And they would be, at this time, this is where the damage was actually visible when the storm was having already some impact. And the different curves just mean different starting point. When you are running a weather forecast, you have some initial conditions, and the global forecast for entire continent or for entire globe is available for anybody to download. So this is something which is prepared on a number of inputs, you know, whether satellites, measurements, weather balloons, surface stations, etc. It's all combined together, and there is a forecast produced, and it can produce with different length of time. And I believe that we were able to make a successful prediction that there will be dangerous amounts of ice accreted up to 5 days ahead of time. So this is a huge lead time, which is very useful for the utilities to take into account and to take some preventive or mitigative actions to deal with this type of problems. Yes, please. You can prevent it, but you can do two things. First, there are ways the utility would have to be ready for that. But for example, they can disconnect the lights for a short period of time and run DC current instead of AC current. So there are methods how to do it so it heats and melts it. If you cannot do that, then you can at least supply, let's say, diesel supply, you know, some power stations of this nature, which can be used at the community so they are not without power for too long. It's really just dealing with the damage in a sense, right? You cannot really prevent it. Another example is forensic studies. This is again something what we did in my lab. This is in Massachusetts. It was the main epicenter of this event. Quite often, the utilities will be sued by their customers, whether industry or individuals or groups of individuals, which of course are affected by that, right? So they may be interested, can you hintcast what would be the epicenter? Could we have done something differently, right? So it's the same exercise, but kind of looking back. And this is again of a great interest to utilities which are distributing and transmitting the power. Very similar application in the sense that we will be using the outputs of numerical weather prediction model, so weather forecasting model, but we are going to use it in a very different way, still with the power lines, but there is something which is called ampacity or transmission capacity. You can imagine that everything has their limit, the same, the wires in the power systems, in power transmission distribution systems, would have capacity, how much current they can carry. And of course, the most determining factor is the current itself, because it will heat the transmission line or the wire. And if it's heated too much, it can eventually melt. It's probably not going to happen, but it can become brittle. It can elongate and it can sag and it can, let's say, touch the trees or houses. Right? So this is something which we want to avoid. At the same time, if I can maximize the amount of power I can transmit, I can take advantage of it. Let's say there is a shortage of power, and if I know I have some hidden extra capacity, I can use it, although it may be above the standard preset value of current I would normally carry. What's normally done, power utilities would be using something which is called static thermal rating, and this is indicated here by this red line. But if I know what are the ambient conditions, so in addition to knowing how much current I carry, I can rely on the weather to do something for me or against me. So if there is windy weather, the wind will cool the lines, so I can actually increase the capacity. On the other hand, if there is a lot of sun and it's hot outside, the ambient temperature is high, it will work against me and I will be able to transmit less power. So the same exercise as before, we would run the numerical weather prediction model. We would follow what's happening at every time instant. And we would solve equations. Again, this is a model which exists, but it was never before connected with the numerical weather prediction. We can actually determine what is the actual capacity, how much current I can actually carry because of this condition. So we can see it here in time on that blue line, and we can see that usually it's quite a bit higher. There are situations, let's say here, when it's even dips just below. This is a danger situation when I shouldn't be using my transmission lines fully. Otherwise, I'm kind of damaging them. It's not going to be immediate damage, but I'll shorten the lifetime. So this is one thing in terms of space. In terms of time. In terms of space, we can look at a similar figure here. And if you would look at that model, which describes the actual transmission capacity or the temperature of the wire, you would see that it includes some of the variables I've already mentioned. So it will be wind, it will be solar radiation, it will be ambient temperature, but it also includes wind direction, right? So it depends if the wind blows along the wires or perpendicular to wires. So we can see this is actually a real-life configuration. Again, it's in the same region. We worked with the utility from Newfoundland and Labrador. And it's a major power line connecting one of the big power plants with the city of St. John, which is the capital of the province. And we can see very nicely here that there could be segments of the power line. So they'll be perpendicular to the wind speed, like when we blowing this way, which are green, meaning that the temperature is relatively low, and there will be some which will be hot, right? And those will be predictable. So even if they knew that, or they realized that, I'm sure that they knew, when they were designing the lines, maybe they could have done something differently, right? If you look at the values, again, it's quite significant. This is the same situation here, and it ranges from ability to transmit 1500 to, let's say, 2200 amps over that over the transmission line. Right? So what we did is one example. The other example, again, just to illustrate why this may be important. We also worked on the other coast, on the Pacific coast, with a utility from Vancouver, British Columbia. And there is an inlet. You can see that this is a small piece of land, which is basically at the sea level. And on the left-hand side, you cannot see it here, but this is a hill, which is quite tall. So the transmission line really goes steeply up, right, from basically 0 to 1,000+ meters. And because there is ocean in between, you cannot put a transmission tower there. So this is a very long span. And due to that length, it's very important for them to know what's happening and what to expect. This is why they install this device, this power donut, which is measuring the current and can measure the temperature as well. But they were interested in predicting that, right? So again, so they can control how much power they are going to transmit. Let's go next. I have few places when I have those yellow slides looking at enabling technology for weather forecasting. And this kind of shows that this is the situation on the left, which is the current way most numerical weather prediction methods are used. This is just the traditional approach, physics, etc. And all the way to the right, we can see that it can be, in theory, entirely placed by a deep neural network, right? most of you heard about deep neural networks. If you didn't, they are responsible for very helpful functionalities on the web. For example, different types of search, image matching, including the deep language models, which we heard about in the news and in the stories very much lately, are based on deep neural networks or deep learning. So similarly, we can expect that we should be able to completely replace the functionality of all the physics by a black box with a deep neural network, right? And I said it intentionally, it's a black box. So if you go to the next slide, there are some things to consider. I'm not gonna go through most of the details, but one important aspect is that it can misfire, right? It can make mistakes. And again, we've heard about deep language models causing harm or certainly providing incorrect information. This could happen here as well, right? And it's about very important critical infrastructure system when we are trying to apply numerical weather prediction, let's say to controlling or to operating power transmission system. So we need to be aware of that. It has to be well tested. There has to be some mechanisms added. If I was going to use deep learning based model for weather prediction, what are the risks and how I can mitigate them, right? But it's very similar to any application of artificial intelligence. In the last part, I'm going to look at some applications in the area of power distribution and energy management. This is the first example where we looked at how we can actually take advantage of electric vehicles, right? In my opening, I mentioned that electric vehicles are likely to cause a lot of problems, and they probably will, because we need to charge them. If everybody is charging them at the same time, it's a big issue. It's not only about not being able to supply the energy to others, right? If you triple the consumption of your house by charging two vehicles at the same time, it's a big problem. But also the system is just not built for it. It can overload, it can be damaged, there could be some big issues. On the other hand, we can consider a situation when we can take advantage of having EVs, and this is specifically for different types of buildings, which typically, if you look at a typical office building or commercial building in a city, there would be dozens or hundreds of users, and if most of them or significant portion of them would have electric vehicles, they can actually help to supply energy in the case of shortage. There are situations when the power supply is interrupted, and most of those buildings may have, some reserve power system, typically again powered by diesel. But if you would assume that you have enough vehicles parked in the parkade of that building, then by having some agreements with the users, you can actually rely on it and you can supply the building with the power. So those four graphs are looking at different types of building for residential building. So let's say apartment building versus commercial building. The nature is very different. You can see that the white squares here are good because this is where I can actually supply a lot of power. And this will be overnight in residential building, right? Most people would be home between hours of midnight and 6, 7, and they'll come home in the afternoon. On the other hand, in the commercial buildings, schools and others, there'll be people coming to work or to school during the day, and we will have enough of those types of vehicles available. Again, by setting up a proper incentive program, incentivizing the users to allow to use your battery in case of emergency. Again, those are things which do not happen every day, but they may happen several times a year. And if we have programs like that, we can rely on it. It depends on the need, and the data is actually, those graphs are generated based on the typical use of traffic. So we took some database survey of household travel using conventional vehicles. We just assumed that they would be EVs and what it would mean for those types of buildings. People may be considered, in that example, which I just used, that case, about the privacy of their data, right? Whether students or workers or employees in a building may be concerned about, maybe they are telling me that they want to use it for reserve power, but maybe they want to watch me when I left the parkade and when I'm back, right? There is one AI approach, which is called federated learning, or in this case, it could be federated forecasting, which actually allows me to do it without compromising the privacy of the data, right? It may not be the only reason, that was just an example. But in this case, and again, this is something which we did with the local power utility, we wanted to forecast electrical load for a neighborhood, so hundreds of houses together, and for individual houses as well. But we wanted to do it on the side of the utility without the utility having direct access in real time to the measurements, right? Of course, utility needs to know how much power you consumed in a month so they can charge you, but they not necessarily need to know all the details. And this approach actually allows that. So there is a central server, which will be on the utility side, which will keep the model, but the model will be updated based on information which stays at the clients. It never leaves that. It's never submitted, provided directly to the utility, to the central server. The server will share the model form and parameters, and the users, the clients, will only update the parameters of the model. And they, in most cases, it can be done in a way that they do not describe anything specific to the user side. Another example, and it's the second last case, I believe, I have two more, is how we can actually improve capacity of distribution systems to accommodate more electric vehicles. Again, we worked with the local utility to identify some situations. The basic idea is that the distribution system is organized as a network, but there are some subnetworks called electrical circuits. And typically, the curve of consumption, the load over time, won't be the same in all of them. We can have a residential neighborhood, we can have neighborhood with shopping malls and hotels and banks, and we can have another circuit in the same proximity, right? They'll be neighboring one another with maybe some kind of small industrial production, even in the city. And because they will have different nature of the load curves will not be synchronized, we can think about mutually borrowing the power when it's needed, and this way to accommodate more electric vehicles. The way the power system is typically organized, it's usually connected in a circular fashion, but there will be also some points which are normally open. So this is the normally open switch. Those are the circles which are not filled. So those circuits will be normally disconnected. I can think about connecting them in a controlled fashion and sharing the power. So I'll connect the switch, I'll connect the two circuits if it's possible. And this way I can share the power. Here we also added battery system. So those would be like the container, half container size, not too big. Battery energy storage systems, which should be connected at those normally open points. So those are 3 locations here. And we would consider this example. Those are real values provided by the utility. We have 4 circuits. They have certain number of transformers, which are transforming the power at, let's say, level of a block of houses or multiple buildings. And we have the levels of maximum, minimum, and average load. And we can see that they are not really very even, especially in those extremes, right? So let's say the minimum goes from 56, 100 kilowatt hours to 7.4 megawatt hours, and similarly for the average load. And what we did, we also considered different levels of EV penetration. So what would be the percentage of electric vehicles installed on the grid? And what we found is that this approach, just with the battery energy storage system like this, can actually quite a bit help. Those are the 4 curves. It's an example just taking for one day, typical day when things will be visible. And we can see that the original load, right, which the curve ends here, would be significantly increased. This peak is quite a bit higher. It goes about more than 8,000 from 6,700 before. If we would have 30% of electric vehicles, right? Using the optimal size and location, so we use some optimization process to do that, we can actually shave shave this even out the peaks and quite significantly lower the peaks, which can cause problems. It can overload the system, and it will prevent more electric vehicles to be integrated. The next step was from this case to consider a new device. This is something which is now subject of research. Many people are looking at it. There is no commercial device which can do that yet, but it's a quite fancy device called soft open point, which actually connect two circuits, so bus A and bus B, using power electronic converters. And it can do a lot of things, right? It can route the power in different ways, so it can go in both directions, and it can make decisions about charging or discharging the battery, possibly with participation of the direct connection as well. So those are all the possible power flows which can be achieved using this device. And we, again, with the same utility, worked on this example circuit, right? Actually, in internal structure is not important. We can see that there are 4 circuits in this case, A, B, C, D, and there are 7 possible locations of connecting those devices, deploying those soft open points on the system, and they correspond to those normally open connections. So there is infrastructure to connect the lines, but they are normally disconnected. If we go to the next slide, we would see that we again run some optimization exercise. And we were looking for what would be the best location for installing some of those devices so we can increase the level of electric vehicle penetration. Those two axes, the number from 0 to 7, actually correspond, so it's 0 to 7, but it's 1 to 7, 0 is not there. Correspond to the location of the devices. Just quick jump on the previous slide, just for a minute. So those are the locations, right? So we were kind of looking where we should install it. It's of course not arbitrary, because it depends what is the nature of load on those circuits. Go back. And you can see that there is specifically 3 points. This is very visible on this middle chart, when always location 2 is involved, and it's in combination with either 7, 6, or 5, right? So those would provide the optimal locations for installing 2 devices. And we found that this can actually support up to 30% penetration without any other changes, right? So just by installing those devices, we would be able to increase the penetration quite significantly. We can then go to different levels of penetration and see what would be the level of violation, right? So there is always one thing is overloading the circuit, but there are other things as well which may happen if I connect too many EVs, which will draw power during charging, for example, and can have dips in the voltage levels, right? It can have frequency changes in the system. So it would, of course, show as a flickering of lights or dimming lights at times, or it can actually damage some devices which would be connected, appliances, computers which would be connected to it as well. So starting from this point, then we can consider where should be the next device installed to further increase it. But we really looked at this basic study just at the 2 devices. The next step, going even more fancy, is to look at possibility to reconfigure distribution network. So what we did here, we considered, this is a test circuit provided by IEEE. This would be a structure of a test distribution system, and we would consider how we can connect them in a way. So that's of course not unlimited number of possibilities. Some of them would not work. Some of them do not have the possibility at all. But in general, there could be much more flexibility if we can reconfigure the structure, the graph of the network, right? And so what we did here, we were concentrating on losses in the system. So again, the same goal which I mentioned at the very beginning. We want to make the operation of the system more efficient. And we use reinforcement learning, so it can learn as it goes, if you are familiar with that. to actually controls this reconfiguration, and it contributed quite significantly. It learned well. You can see some convergence curves here, and it was able to optimize the configuration, the actual topology, how the individual nodes are connected within the system in a way that contributed significantly to the lowering of the losses. And the very last example case, it's still related to distribution and energy management, but it's completely different approach. You may have heard about it before. It's called transactive energy. And the idea here is, instead of transmitting and distributing energy over distances, and in transmission case, long distances, why don't we try to use it locally? Why not to have transactions between people who have PVs and batteries and maybe EVs and people who need the energy, right? So if you think about it, most losses are happening in the transmission and distribution of the energy, right, on the system. So if we can not necessarily completely avoid it, that's no worry for the power companies. Nobody's trying to put them out of business. But if you can do more locally, then we will minimize this. And it can also be more economical. So I think the most important diagram here is this one, right? So I would have, let's say, somebody who has electric vehicle, they may have solar panels, batteries, and somebody who would need the energy at the same time. So they can actually exchange on a market, which will be local, to organize those transactions. So people will be bidding and offering energy, and if there is a match, the transaction will take place. This is why this is called transactive energy system. So we've designed such an approach. We were experimenting with different settings for the system. Let me just finish this one. And we found that there is a sweet spot which will actually work reasonably well, meaning that it makes sense, it satisfies some principle for fairness, and it corresponds to some economical principles. Yes. You're using battery, right? And that wouldn't put more hours on battery, and that's for less time for you. So why would people want to give like battery life? It's all about incentives, right? It's the same question we may ask: why would people buy electric cars when they are more expensive? So if there is a right program, right case, it can be done. So if it's controlled in a way that it's not excessive, then there will be always some additional aging or the depletion of the capacity of the battery, but they'll be perhaps compensated for it. Let's say you would be able to sell the power to your neighbor for a little bit higher price. It's still better price for the neighbor than if you would supply the energy utility, right? So from the perspective of both the prosumers, who may get more money for what they generate using their PV or from their EVs or batteries, from the neighbor than from the utility, the neighbor can get lower price again in the same comparison. Typically, there is a gap between what the power utility will buy the power for and sell it for. For the utility, it may look like a bad case, but it's not necessarily, because they may need to make a huge investments if they want to be able to accommodate the increase of PV and EV penetration on the grid. But this can defer it. So they will be saving a huge amount of investments, right? Which they would have to pass to the customers in the end, but it's not an easy case to make with the regulators, government, and with the users as well. So in a sense, it will allow to use a little bit less of that capacity which is available from the utilities in a relative sense, but absolutely it can remain the same. It will just take care of the increased incremental marginal addition caused by the distributed energy resources integrated on the system. The issue which you mentioned with EV, there is, of course, this potential issue. What's interesting is that the EV can actually take the power, charge in one circuit, one neighborhood to another one. So it makes it very, very interesting problem, all right? It can have advantages and disadvantages. It makes it more complex for sure. So in conclusion, I was trying to show you some examples how we can use data analytics and AI to support energy transition. And we've looked at those three larger areas. I've mentioned some leading edge technologies which are really modern, such as deep neural networks, federated systems, and reinforcement learning, which can help even more to address some of those challenges. And I also mentioned that there need to be caution taken to avoid being trapped in a system which will not work well because it was not trained properly, and now we have very little control of what it does, because many of those systems are in the end black boxes. They do something and we do not understand what they do. We can try to add some explanatory ability on top of them. That may be one way how to help, but we always have to be aware of those risks and not to rely on them fully or prematurely. So that's all for me. Thank you for your attention. If you have any additional questions, I'll be happy to answer them. Thank you. Yeah.
Recently, I researched regarding predictive systems, but in paper life, and the big issue regarding that was that those type of systems require controllers and data and experts and those, and that increases the cost. How does this solve that problem? Like, for example, AI and more complex predictive systems, will they be like more expensive? How does that impact on the energy savings or the increase on that?
So I'll start it with the very last point. This is difficult to access, and we probably don't have the data or the experience yet. So this remains to be seen whether it is economical. What's important is enabling. Sometimes you wouldn't be able to do some things without deploying those methods. And as we saw, even in some of the examples which I used today, it was the ice accretion, which is one of the older projects. I thought it was interesting, and it really shows the history. We trained it on one type of system, or even one type of climate, I would say, southern United States versus not very northern, but still much more north in Canada. And they still work, right? So of course, this is to be verified, but this is lowering the cost. You develop it once, and I'm not saying it's the same utility using that, but the knowledge is there and can be used by others if we share it properly. So this is lowering the cost as well. And this is something, the principle of generalization, it's very important in AI and neural networks and other systems, and it's very beneficial, and it really makes things less expensive because we do it once or maybe 1,000 times, but we can then use it 1,000,000 times more. Right?